On February 27, 2026, a machine 15 billion miles away did something it had never done before during a routine, ordinary maneuver it had performed countless times over the previous 49 years. Its power supply dropped. Not gradually, not on the slow, predictable schedule engineers had been tracking for decades. It dropped unexpectedly. In the middle of a simple roll, the kind of small, directional adjustment Voyager 1 has executed thousands of times since 1977, without incident. And for a few tense hours back on Earth, the team responsible for humanity's most distant machine was staring at a very real, very immediate possibility. That the spacecraft's own internal safety system was about to make a decision none of them wanted it to make. This is the story of what actually happened to Voyager 1 this year, the emergency nobody saw coming, the instrument it cost the mission, and the high-risk experiment currently underway right now, this month, that could determine how much longer humanity keeps hearing from the edge of known space. And unlike a lot of what circulates about this mission online, every part of what you're about to hear is drawn directly from NASA's own mission updates and statements from the scientists actually running it. Not speculation, not exaggeration, just the genuinely dramatic reality of what this spacecraft has been through in the last several months. To understand why that power drop in February mattered so much, you have to understand exactly how fragile Voyager 1's situation already was before it happened. The spacecraft runs on 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into a steady trickle of electricity. It's an elegant, reliable system, but it comes with an unavoidable catch. That plutonium decays whether anyone wants it to or not, and the generators have been losing roughly 4 watts of power every single year since launch. Engineers have known about this slow decline since before most of the people currently working on the mission were born, and for decades, they've been managing it with careful, methodical planning, shutting down individual science instruments one at a time in a specific, pre-agreed order, always trying to squeeze the maximum possible amount of science out of a power budget that only ever shrinks. It's worth remembering just how small a margin this mission is actually operating on. Voyager 1 and its twin each weigh about 720 kilograms, roughly 1,600 pounds, machines built with 3 onboard computers sharing a combined total of only 68 kilobytes of memory between them, running on processors, clocked at a mere 250 kilohertz, commands sent up to the spacecraft travel at only 16 bits per second, and the scientific data that comes back down arrives at around 160 bits per second, roughly 500,000 times slower than an average home internet connection today. This is the hardware that has been keeping humanity's most distant emissary alive and talking for nearly half a century. And it is the same hardware that, this year, had to weather an emergency nobody had specifically planned for. By early 2026, that careful, decades-long planning had already claimed 7 of the 10 original instrument packages Voyager 1 launched with. Only 3 remained active, each one still sending back genuinely unique data from a region of space no other human-made object has ever reached. And then came February 27th, a date that wasn't supposed to be significant at all. During what should have been an entirely routine roll maneuver, a standard adjustment engineers use periodically to reorient the spacecraft's antenna and confirm its pointing. Voyager 1's power levels fell by more than anyone expected. Suddenly, the team wasn't just managing a slow, predictable decline anymore. They were watching a number drop closer to a threshold they had spent decades trying to avoid ever approaching. Because built into Voyager 1's design is a system called undervoltage fault protection, an automated safeguard meant to protect the spacecraft if its power ever falls dangerously low. If that system triggers, it doesn't ask permission. It starts shutting down components on its own according to its own internal logic in order to protect what's left of the spacecraft. That might sound like exactly the kind of safety net you'd want. In practice, for a machine this old, this far away, and this impossible to physically repair, an automatic fault-triggered shutdown is one of the most dangerous things that can happen to it, because bringing a spacecraft back from that kind of automated safe mode is a lengthy, uncertain process that carries real risks of its own, conducted entirely through the 23-hour one-way radio delay that separates Earth from the edge of interstellar space. The Voyager team did not wait to find out what would happen if that fault protection system triggered on its own. They acted first. On April 17th, 2026, engineers at NASA's Jet Propulsion Laboratory sent a command across 15 billion miles of empty space, a command that took roughly 23 hours just to arrive, instructing Voyager 1 to permanently power down an instrument called the Low Energy Charged Particles Experiment, known simply as the LECP. This was not a small, symbolic sacrifice. The LECP had been running almost continuously since Voyager 1 launched in September of 1977, nearly 49 straight years of operation. It measured low-energy ions, electrons, and cosmic rays streaming in from both our own solar system and the wider galaxy beyond it. and it had played a genuinely critical role in some of the mission's most important discoveries, including helping scientists pinpoint the exact moment Voyager 1 crossed the heliopause and left the protective bubble of our solar system behind entirely. Kareem Badarudin, Voyager's mission manager at JPL, put the decision plainly. "Shutting down a science instrument is not anybody's preference," he said, "but it was the best option available." Voyager 1 still has 2 remaining operating science instruments, he added, one that listens to plasma waves and one that measures magnetic fields, both still working and still sending back data from a place no other human-made object has ever explored. There's something worth sitting with in how that shutdown actually unfolded, because it tells you just how precisely this aging spacecraft is still being managed, even now, 49 years after launch. The command to shut off the LECP took roughly 23 hours to reach Voyager 1, and once it arrived, the shutdown process itself took another 3 hours and 15 minutes to fully complete. A slow, deliberate sequence, rather than a simple flip of a switch. Even ending something is a careful, hours-long negotiation with physics when you're this far from home. And in a small but genuinely remarkable detail, engineers chose to leave one part of the instrument running. A small stepper motor, whose only job is to physically rotate the instrument's sensor in a full circle so it can scan in every direction, was allowed to keep operating. That same motor had already been tested on Earth, decades ago, designed to withstand about 250,000 steps. Enough to get it through Voyager 1's original flybys of Jupiter and Saturn. By the time engineers made this decision in 2026, that motor had silently completed more than 8.5 million steps in the cold of interstellar space, at temperatures dropping to 62 degrees below 0 Celsius, after its supplemental heater was switched off years earlier to save power. Stimatios Krimigas, one of the instrument's principal investigators at the Johns Hopkins Applied Physics Laboratory, wrote afterward that the stepper motor had worked flawlessly for nearly 49 years. And that watching it continue to function under those conditions was, in his words, the stuff dreams are made of. Now here's where the story shifts from crisis management to something closer to a genuine gamble. Because this shutdown wasn't just about saving power in the moment, it was also about buying time for something far more ambitious. An experimental procedure the team has informally nicknamed the Big Bang. The idea behind it is relatively straightforward to explain, even if actually executing it is anything but simple. After nearly 50 years in the harsh radiation environment of deep space, some of Voyager 1's electrical components are almost certainly operating less efficiently than they once did, which means there may be small pockets of usable electrical capacity still trapped inside the spacecraft's aging systems, a capacity that isn't currently being captured or used for anything. Voltage regulators, wiring, and other components that were engineered with a certain amount of built-in safety margin back in the 1970s may, after 5 decades of gradual change, be holding onto small reserves that the spacecraft's current power management logic was never designed to find or use. The Big Bang procedure is an attempt to restructure how power flows across the spacecraft in order to recover some of that stranded capacity and redirect it toward keeping instruments alive longer than the standard 4 watt per year decline would otherwise allow. It's a delicate kind of surgery, made only more difficult by the fact that there's no way to physically inspect a single wire or component before making a change, and every test carries the same underlying risk that has shadowed every difficult decision this mission has ever faced. A wrong command sent across billions of miles of empty space cannot be taken back. If it works, it wouldn't just slow the mission's decline. There's a real, if cautious, possibility it could let engineers switch the newly shut down LECP instrument back on. Given how much is riding on this and how little room there is for error at this distance, the team didn't go anywhere near Voyager 1 first. Instead, they tested the procedure on its twin, Voyager 2, which has slightly more available power in reserve and sits somewhat closer to Earth, making any potential failure marginally less catastrophic to the overall mission. Voyager 2 reached interstellar space in 2018, 6 years after Voyager 1, taking a different, slower route that carried it past Uranus and Neptune along the way, making it the only spacecraft in history to visit all 4 of the solar system's giant planets. That extra distance behind its twin and the slightly different power situation it's ended up with as a result made it the safer of the 2 probes to risk first. Those tests were scheduled for May and June of 2026, and if those tests went well, the plan was to attempt the same fix on Voyager 1 itself no earlier than July of this year. That timeline is not a future prediction. That is happening right now. As I'm telling you this, the Voyager team is either in the middle of that Voyager 1 attempt or preparing to begin it, marking one of the highest stakes engineering procedures this nearly 50-year-old mission has faced. Matt Hill, the LECP's principal investigator at Johns Hopkins, described what the instrument meant to the mission's legacy and what its possible revival would mean going forward. With LECP, he wrote, scientists discovered properties and effects of cosmic rays and solar particles, and used it to sense the changes in the surrounding region that determined exactly when Voyager crossed from the solar system into interstellar space. He said the team is holding out hope that this latest plan could power the instrument back up on Voyager 1, letting it continue learning whatever surprises still await the spacecraft in these genuinely unexplored regions of space. But he was also honest about the odds, adding that the Voyager engineers have built a remarkable track record of pulling off what feel like small miracles to stretch the spacecraft's remaining power supply, while acknowledging, in his own words, that eventually that streak will end. That's really the emotional core of everything happening with Voyager 1 in 2026, and it's the part I think deserves more attention than a single news cycle usually gives it. This is not a mission quietly winding down on a smooth, predictable curve toward its final silence. It is a spacecraft that just experienced a genuine, unplanned scare, an unexpected power drop during a routine maneuver that pushed the team closer to an automated emergency shutdown than they had ever intended to get. It responded by making a hard, deliberate sacrifice, permanently retiring an instrument that had operated for nearly half a century. And it is now, this very month, attempting an experimental fix that nobody has ever tried before on a spacecraft this old, this far away, and this impossible to physically reach if anything goes wrong. And all of this is unfolding while an entirely separate milestone bears down on the calendar, one that has nothing to do with any of this uncertainty and is going to happen regardless of how the Big Bang procedure turns out. Sometime around mid-November of 2026, Voyager 1 will cross a distance of exactly 1 light day from Earth, roughly 16 billion miles out, moving at around 38,000 miles an hour toward a point in the constellation of Ophiuchus. It will be the first human-made object to ever operate at that distance, adding to a list of firsts this spacecraft has been quietly collecting since long before most of its current engineering team was born. It was Voyager 1 that captured the first close-up images of Jupiter's volcanic moon, Io. It was Voyager 1 that, in 2012, became the first human-made object to cross the heliopause and leave the protective bubble of the sun's influence entirely, after a journey that included flybys of Jupiter in 1979 and Saturn in 1980, the very encounter that gave the spacecraft its last trajectory correction burn. It hasn't fired a thruster to adjust its path since. Everything since Saturn has been pure momentum, riding the exact gravitational assists it picked up during the Carter administration, coasting through the dark on a trajectory locked in nearly 46 years ago. At that distance, a radio signal traveling at the fastest possible speed anything in the universe can travel will take a full 24 hours just to reach the spacecraft, and another full day for any response to make its way back. Voyager project manager Susie Dodd has described what that actually means in practice. If engineers send a command at 8 in the morning on a Monday, or they won't know whether it even arrived until Tuesday morning, and they won't receive Voyager 1's response until Wednesday. No human-made object has ever operated at that kind of distance before. Voyager 1 is on track to become the first, while it is still alive, still speaking, and still, as of this month, in the middle of an experimental procedure that could determine just how much more it has left to say. So here's what I want you to actually take away from all of this, because it's easy to talk about Voyager 1 in the abstract, as some distant, almost mythical machine drifting silently through the dark. What happened this year was not abstract. On a specific day in February, during an ordinary maneuver, the spacecraft had performed without incident for nearly 5 decades. Its power behaved in a way engineers didn't expect. And for a few genuinely tense hours, the team responsible for it had to move quickly to keep an automated safety system from taking control out of their hands. They succeeded. They made the hard call, sacrificed an instrument that had been running since Jimmy Carter was in office, and bought themselves room to attempt something that has never been tried before on a spacecraft this far from home. That's really the part of this story worth sitting with the longest. This mission has survived nearly 50 years by being managed, not by luck. Every shutdown, every reroute of power, every decision about which instrument lives and which one goes dark next was debated and agreed upon by a small team of scientists and engineers years in advance. Exactly so that when a moment like February 27th actually arrived, nobody had to improvise under pressure with 15 billion miles and a full day of radio delay standing between them and the machine they were trying to save. The emergency was real. The response to it was not panic. It was a plan, built years ahead of time, finally being put into action exactly when it was needed. Whether that experimental fix succeeds or not, Voyager 1 will keep moving, keep transmitting whatever power allows it to transmit, and keep closing in on a distance no human object has ever reached, carrying with it 2 working instruments, a golden record, and a small stepper motor that has already quietly outlasted every reasonable expectation anyone ever had for it. If you want to know whether the Big Bang procedure actually works, and whether that decades-old instrument comes back online, subscribe and turn on notifications, because that answer is likely to come within the next several months, and we'll be covering it the moment it does. Drop a comment telling me whether you think engineers managed to pull power back from a machine built in the 1970s. Because if the last 50 years of this mission have taught us anything, it's that betting against Voyager 1 has never once been the smart move.